Welcome to the course. I am Lodovico Giaretta, and I will be uh, beginning this with a general introduction to MLOps. But before that, yeah, just again, by brief setup info. As David mentioned, the workshop is recorded. Stay off with the camera and mic, and we might do editing in the end if you pop up. But yeah, try to avoid popping up in the with the camera and mic if it's not necessary, then it will not get recorded. And for questions, this is an interactive session. We will take a few questions, in particular in between sessions, depending on time. If you have a lot of questions, you can also absolutely write them in the HackMD. And if you do so, answers will appear there automatically. So that is a good way to keep the time and make sure that we are able to see and answer all of the questions that might arise. So yeah, having said that, let's start. So the agenda for today, very approximate. Don't expect that we will actually follow this, but we will start with the first part about what is MLOps and what is the big picture idea of MLOps. And then Anders will take over to go step by step into the various components of an MLOps pipeline. And we will have some short breaks in between. Again, the times are subject to change depending on when exactly each section ends and how is the flow with everything. So yeah, let's start. And the very first thing I would like to ask is if you can all open the HackMD Q&A document, and you will see there is an icebreaker section with these two questions. What is MLOps and what are the components of MLOps? And please write down briefly the answers there that come to your mind. So what do you think coming into this training event? What do you think is MLOps, and what do you think are the key components to achieve it? Okay, I can see some entries coming in. So for what is MLOps, I can see some people are writing AI lifecycle management, bringing ML models into operations, orchestration, CI/CD for machine learning. And for the components of MLOps, I see people mentioning model registry, training data, models, parameters. Let's see, more answers are coming in. ML implementation in a large-scale real-world process. For what is MLOps? And for the components, also good data, and then training, evaluation, deployment, monitoring, ML algorithms. Okay. I think these are some very interesting, very interesting points and uh, answers that you provided. And I think it's very good starting point because you are all going in the right direction, but also there are quite some differences in what you're writing. And that is kind of one of the challenges with MLOps. And the challenge is that there is no one clear definition that wins over all others, one standard definition of it. There are a lot of different takes and different opinions on the matter. So the way that I like to think about it and introduce MLOps is that MLOps is, and I mean, this comes also from where the names comes from. It's a little bit like thinking DevOps, but for machine learning projects. And what do I mean like that? So what I mean is that when we think about DevOps, what did DevOps achieve? The idea of DevOps, the problem that DevOps was trying to solve, one of the problems that DevOps was trying to solve is that traditionally you'd have a software development team, and then you'd have an operations team. And the development team would develop a product, and then once it was ready, give it to the operations team, and the operation team would actually run this software, run the product, deliver the service on top of this product. But this approach with two separate teams being responsible for the two different phases brought a lot of challenges and a lot of friction at the interface between these teams, right? Because now the development team needs to deliver to the operations team, maybe on a certain schedule, and any metrics, any feedback collected by the operations team then need to be somehow given back to the development team. And when something goes wrong, it might be unclear who is responsible for what and who should communicate what to whom or address which issue. So there's a lot of friction that arises with that. And DevOps, the idea was let's have one team that will be responsible for both the development of the service and the operations of the service. Bring both of them under one roof and remove this interface between different teams and be able in this way to have a faster and more streamlined process. And the idea of MLOps is the same, is to bring the whole ML process under one roof, within one single process, within one team or one organizational unit of some sort. And not have this distinction between the team who builds the model and the team who runs the model. And again, to avoid this issue of feedback loops, of communication interface, of taking ownership and responsibility for different parts. So it makes the whole development and the release cycle much, much faster. And then the second thing, though, is that once you have all of these under one roof, once you have one group that is responsible for the whole process, now you can build a workflow. You can build a set of best practices connected together in a clear structure that spans the whole process. So you can have an MLOps flow that spans from the development all the way to the operations and back in a unified way, with following all the best practices that are available. And what this leads to, all this good, strong, comprehensive structure then leads to a lot of benefit in terms of being able to have comprehensive automation of the whole process, reliability in how the process is performed thanks to automation, reproducibility also gets boosted, and governance gets boosted due to better visibility into the entire flow of operations. So this is sort of what is it that MLOps gives us. This is what MLOps promises us to deliver. But then the question is, what do we do? How do we do it? How do we actually achieve then this MLOps flow? Once you've broken down the barriers and put everything under one roof, how do you actually structure this flow for MLOps? And this is where we can think about the second question that I asked you after what is MLOps, which is what are the components of MLOps? And here, what happens is that a lot of people, when asked what are the components of MLOps, come up with a few come up with a few components within a flow. And how this might look like is you have some data. This is the data that you should use to solve the problem you're trying to solve. It's some existing data source, possibly more than one, that is somewhere. And the first step of your MLOps flow is you start by fetching and exploring this data. You look at it, you see how it looks like, what kind of information you have there, what kind of structure it has, and then you proceed to data cleaning and data processing. How do we prepare this data properly for our model? And once you've done this, once you prepared your data, you want to train your model, right? You train your model, you do maybe some hyperparameter tuning of your model to find the best set of hyperparameters for your model. You run some evaluation, so you check how the model performs. And you will, of course, this is not just a thing that you do once. There's going to be, of course, this is the machine learning loop after all. So you will have some looping back. After evaluation, you might go back and rethink how you prepare your data or rethink how you train your model or how you do hyperparameter tuning. And then eventually, you might have a model that at the evaluation stage performs pretty well. And therefore, you might decide to deploy this model into production. And so you might end up with this, where you take your model and you put it somewhere for inference, where it will take new data as input coming in from somewhere, and it will produce some outputs, typically some predictions. This is what typically people think about. And I can see that some of the components that you mentioned are indeed these components, right? Training, evaluation, deployment. But there is more to MLOps than this. This is actually very, very incomplete of a picture. And this is the first, I would say, takeaway for you is that if people tell you that this is what MLOps is about, they are wrong. This is not enough to achieve MLOps and to fulfill the promises of MLOps of giving us automation, reliability, governance, and a faster cycle to develop and optimize our models. This is incomplete, and this is, we could say, just what I would call the inner loop of MLOps. This process of cleaning the data, training the model, evaluating the model, this is a core inner loop for any machine learning project. And it's important to master this loop because it appears over and over and over in any machine learning project and in any MLOps workflow. However, it is not MLOps. This is not sufficient. So what are actually the MLOps components? And the key point here is that we want to have a process that covers the whole project from start to end. And we want to unify all of it in a proper framework. So where do we start actually? And this is something that this first step is something that a lot of people don't think about. The first step is project definition. This is where you go and you actually work with stakeholders. So people outside your data engineering, ML engineering team to understand what is the problem that needs to be solved. And this is already a very challenging step where a lot of things can go wrong, a lot of pitfalls can happen here. I will not go now into the details of that. Anders may have more on it later. But the key point is here we should understand what we're trying to do. And what we want to achieve is we want to define what is the task that we are trying to solve, and what data we should use, and what metrics are important. This is the very first step. So we start and we have our project definition, and we have an idea of what is the data that we want to work with. But then we need to go to the next step, which is that of exploration and development. And this is actually what many people think about when they think about MLOps. This is where we find this loop that I showed before: data exploration, data cleaning and preprocessing, model training, hyperparameter tuning, model evaluation. This is this process, where this process lives in the most clear fashion. And the key thing here, see this human in here, this is very much a human-driven process. This is where your data engineers, your ML engineers, this is where the people actually perform the development. Going in loops, looking at different options for how to clean the data, which types of models seems the most appropriate for the data, which type of data processing approaches, how the evaluation process looks like, how the evaluation metrics look like, maybe some early hyperparameter tuning to see what is the space of hyperparameters, the space of options that I should think about, that are relevant to explore for this problem, and which instead seem to be very bad and we can ignore from the very beginning. And the goal here is not to come up with a model that you can deploy for inference. That is not the goal here. The goal here is to figure out what is the correct approach to build a model for production-grade inference. And therefore, the output of this step is not actually a machine learning model. The output of this step is a blueprint for how we handle the data and how we build and evaluate the machine learning model. So the output of this step is actually mostly code. So what will happen is that you will take your task definition, you will take your data that has been defined, and you will produce code that will enable you to train, to process the data, train the machine learning model, and evaluate it. So you produce the code for your machine learning pipeline. This is not your main machine learning pipeline. So you produce the code, and then you store the code somewhere, typically in a source control system like Git, so that it gets saved and versioned. And this loop can happen, of course, multiple times over. You might have different approaches, different versions, different pipelines that you come up with. And then the next step when you have this is, okay, now that I have this code, now that I have this blueprint for how I build a good machine learning model, this is when we actually switch to production. And this means that we switch to the production pipeline for building models, for building machine learning models. And this is supposed to be a fully automated process where humans are ideally not involved at all. And it is purely based on the blueprints that were built in the exploration and development phase. So those blueprints, that code gets automatically executed and used in a structured way to perform the data processing, train your machine learning model, and eventually produce a model that is ready to be deployed for inference in production. That is the goal here. And the steps that this does, as I already mentioned, it takes the data and it performs cleaning and pre-processing, machine learning model training, and also hyperparameter tuning, if so you desire, and it evaluates the model that gets produced. And the key point again, these are not coming from manual input, but these are coming from the blueprints that were already developed. So this is how the process looks like. You build production pipelines that take from the blueprints that were built and use that code. So the pre-processing step here will be taken from the code and will be the pre-processing step that you defined and that you found out during the exploration, during your iterative exploration phase, that this was a good pre-processing and the corresponding good model training and hyperparameter tuning code and the corresponding good and strong evaluations. So I will take a very short break here to give you a chance to ask questions. Are there any questions on the process so far?
There is one in the HackMD. Won't this cause human-related loop in the exploration and development part? It may have to be elaborated a little bit.
Yes, this might be to be elaborated a little bit, but yes, this exploration development is very much human-driven. So I guess this goes against my previous point of automating everything, right? In which case, yes, this first exploration development phase contains some human action. At some point, a human needs to try out things, I would say. One could argue you could do some sort of AutoML where a human never needs to do anything, but that has significant limitations. So in any large-scale process where it's really important to get good results at scale for complicated problems, there will need to be a human involved in this exploration and development. In the same way that when you develop software, until very recently, you would need to have a human writing the software. But the idea is that everything else should be automated. A human should not have to handle the production level training and evaluation. And that is the key point here, right? We start with a playground where the humans, the experts, can build things, but then the actual model you're going to use in production has not been built here. Because this is very dynamic and it's very hard to track what happens in here, what different people try out. So instead, we build our models in an automated production pipeline that is based on versioned blueprints that we stored in our source control system, in our version control, so that we know which version of the code is used to build which model. And this then very well brings me forward to the next point I want to present, which is what happens once you build your production pipeline. And the production pipeline has now built the model for you. So it has performed the data cleaning, trained the model, found the best hyperparameters, and evaluated the performance of the model. Then now what should happen is that this model is ready to be sent to inference if it is good enough. So how do we do that? Well, what we do is that we package the model together with the blueprint to run it and its evaluation result and put it into a model registry. So in the same way that after the development phase, we store and version the blueprint to build models. Then after we use the blueprint to build models, then we also store and version the resulting model, its own blueprint, and its performance characteristics. And it is then from this model registry that we pick a model to bring to inference. And this is again an automated process, again blueprint driven by the code that we have. And what will happen is that it will take from the model registry a model that has been produced by our production pipeline, not by humans. And it will take this model and it will push it to inference. And note one key thing here, it doesn't just bring the model to inference, it brings the whole blueprint, including the cleaning and pre-processing step. So you have the data coming in, it gets cleaned, pre-processed, inference is performed on it, and you get your machine learning model output. So this is then the overall big picture of your MLOps flow from start to end. You start by defining the problem, finding the data. Iteratively, you figure out what are the good blueprints to solve the problem. You then bring this blueprint to a automated pipeline that will build a model, evaluate it, store it in the model registry, and deploy it for inference. And the key point here, the final key point, the final key piece of the puzzle is that things don't actually end here. Things continue because it is never the case that you deploy a model for inference and it is done. It is never the case that you bring a model and that model will now, for the foreseeable future, until your company goes bankrupt, deliver great service to your clients, if that is what you're doing. Rather, this that you just deployed is just the first production deployment of a model. You will have to deploy new versions of this model over time, which means that over time, you will need to do more of all these steps. And this is where what is very important are the feedback loops that we have between different components. The feedback loops that enable us to iterate this process and to provide this quick iteration that would not be possible if these components were performed by different teams and not set in a unified workflow. So what happens is that we have all these different feedback loops. So what could happen? What could happen is that, well, you define a task and some data, but then when you go into the exploration and development, maybe you figure out that the task is not sufficiently well defined, or the data is not good enough to solve the task. And then you need to go back to the drawing board, redefine the project, find different data. Or maybe what happens is that this goes well, you go to production, to the production training pipeline, but you actually find out that what maybe looked good looked good enough in your initial exploratory development phase, when you actually maybe scale it up to more data in the production pipeline, it actually doesn't work as well anymore for some reason. And then you cannot deploy it for inference. You need to go back to trying to improve it. Or maybe what happens is that you deploy the model to inference because it is actually good enough. It performs well enough. But it will not perform well enough forever. You actually need to keep monitoring what is happening in production. Is the model performing well? Is the model performing up to expectations? And if the model at some point stops performing up to expectation, then you need to deploy a new model. And how do you deploy a new model? Well, there are two ways here. One way is the fully automated way. If the model is no longer that good, maybe it needs to be trained on more data. So maybe what we can do is that we can actually just go back and retrain the model automatically, going from the automatic deployment back to the automatic training of the model through this pipeline, which will then register a new model that can be fully automatically deployed back to production for inference, which means that you have this closed loop, fully automated closed loop that keeps the model updated, keeps deploying new versions of the model as needed to maintain a high prediction accuracy. But sometimes this is not enough. Sometimes it might be that actually to keep your model up to date, you don't just need to retrain it. Maybe you need to rethink it. Maybe you need to change how the model works, change how it processes the data, or change the structure slightly. Maybe it's time to switch to a bigger model because we want it to do a slightly more complicated, provide slightly more complicated or more accurate predictions. So you might go back to your exploratory and development phase and come up with a new blueprint that will then trigger again the automated flow. And this is, I would say, the key component. This, I would say, is what really is hard to master and allows you to close the loop and enable a true MLOps flow that really gives you all the promises of MLOps, of faster cycles to build and deploy your model, of higher reliability, higher accuracy, better governance, and more visibility in how the whole process performs and how decisions are made and how automation is triggered. So yeah, this is basically the high-level view of the MLOps process. I will stop again for questions here. Let's see if we have some in the chat. Are we keeping track somewhere of the intermediate models that we built during the development phase? Someone asked in chat. Well, sometimes the process is very much ad hoc, but very often people do use experiment tracking software where you can track individual experiment run that you have even during this exploration development phase. And the experiment tracking software is in essence a subset of what a model registry offers. A subset of the model registry functionality is the tracking of experiments, tracking of metrics, tracking of model checkpoints, and that can be used in this exploration and development phase. But again, that is mostly a way for the human involved in this part to reason about what works and what doesn't, about what has been tried, and to inform decisions for the next iterations of this loop. That is effectively what is happening there. It shouldn't be used for controlling the automated phase. That should not be done from the experiment tracking. Then let's see. When the model gets outdated, is there a way to insert a monitoring module to help the model maintenance? Yes. So, or no, depending on what you mean. But yes, you absolutely need monitoring to be part of your inference setup. And that is a tricky part that we'll go into a little bit more again tomorrow. But because it's tricky to do monitoring, it's not easy. Like, how do you do it? What do you monitor? And some things might not be trivial to monitor, like if you are making a prediction about the future, if then you cannot immediately get information of whether your prediction was correct or not. Then you need a way to, in the future, when the correct answer is available, to match it back with what your prediction was and decide whether your prediction was good enough or not. For example, if that is what you want to measure. So there are different kind of metrics that you might want to collect that require different techniques. But yes, and those metrics will be what drives this backwards feedback loop, right? Where you go back when the metrics are no longer good enough, you can go back to your production pipeline or even to the development phase. And then there is a question, what are the good books to master MLOps from intro to higher levels? I do not have an answer to this question. If someone has, feel free to write in chat. I do not. But we can take, I would say, a short 10 minutes break until 10. And then when we come back, I will leave the floor to Anders, who will now go into a little bit more details about a lot of these steps that we just mentioned. So we just looked at the big picture, how the process as a whole looks like. And now with Anders, we will dig deeper and see what are some of the key things to consider, some of the key pitfalls and the tricks and the questions in many of these individual phases and individual steps that we have.
I will repeat some of the things that Ludovico said. So first, just it's obvious to everyone that this is a misconception about machine learning now, but just anyway, this is what some people out there, not anyone in this course, but some people might think that you don't need to understand your data nor the task you are solving, because the models, machine learning models, will do that for you for sure. So just test all possible models with scikit-learn and all possible hyperparameters, do a grid search of hyperparameters, and then pick the model that works the best, and then you are done. That's and maybe I pointed a little bit, but this is sometimes you feel this thing, and as Lodovico went through, a more, at least partially more realistic flow might be something like this, that you, of course, you need to properly first, the first step is actually, you never start with the data. You need to understand your task, what you're going to solve, and if there is any data, hopefully there is, how does it look like? What does it mean? How good quality is it? And so on. And then comes this long step of cleaning, fusing, selecting, pre-processing, representing the data in a, preparing it in a nice way for the machine learning. And then a minor part is selecting the model architecture. It's important, but it's not, people might think it's the main one. Check all different architectures, but this is usually the faster part, and the selection of hyperparametric training and so on. This is what was mentioned. And then comes this big part again that Lodovico hinted, this package it all put together to become automatic, make sure to document it because it's not the last time you will look at this. It's not something you just leave behind you. You have to go back and everyone forgets quickly. And then this deployment, make it actually work for real. And then that's not the end, as Lodovico also said, but this is when you finally will know if it actually works. You might think it works after doing the validation, but this is now when the real complications can pop up, and it is an iterative process. So probably if it doesn't work as you expected, then you have to go back through the entire process several times. So the first 4 bullets I will hopefully cover today, and then there will be more both by Lodovico and me tomorrow on the rest, I think. So, and then I want to start not from the beginning. I will actually start with the third bullet, the model architectures. Because as you know, there are many different machine learning paradigms even, not and each with several different architectures. So just to go through them quickly, some of them, you may know that there is, So these are the 5 paradigms that I'm thinking of actually. You might, even though artificial neural networks is the one that gets the most attention nowadays. So I would say that the simplest one to start from the beginning, just case-based methods. The idea there is simply it's a kind of table lookup, save all the training data, and when a new sample appears, find the ones that are closest to it in this among all the saved training data, and then assume it has the same class, kind of. So okay, then I should have said this. I did not. Let's see. The important thing to say here is, of course, that here I assume with machine learning method, you have a number of training data, and then you have then you will get, when you use it, you will get new samples of data, and then you want to make some conclusion about the new sample based on the training data. That, of course, I could have. That's a general machine learning idea, and So case-based methods anyway, then you say that the closest match is the same class as a new sample, kind of. And one example is k-nearest neighbor. That's one you probably heard about. Let's just quickly, I shouldn't dwell so long on each of these, just so you have an idea. Logical inference, that's the class where actually random forests and XGBoost and all the methods, they are usually based on this logical inference, building on creating logical expressions for the different classes, and then usually forming ensembles out of them. And then the artificial neural networks that you all know about, you have several layers of nodes, and more or less layers of nodes, more in the deep neural networks, less in the less deep ones, and with weights between them, and you train them by iteratively adjusting the weights to get more and more correct results on your training set. And there are, of course, many examples. There are specifically many examples of deep neural networks nowadays, convolutional neural networks, autoencoders, and transformers, of course, but LSTMs, variational autoencoders. Yeah, I can list. There's a long list of them. But then we have an equally large category of statistical machine learning methods that is actually still also very useful. For example, Bayesian classifiers you may have heard about, mixture models, graph models. Markov chain Monte Carlo is an important method, often used, but also things like just linear regression. So the statistical methods, the key idea there is, of course, to try to, from the training data, try to estimate your the distribution of the class given the input features. So look at it as a probability distribution. And then, of course, there is one final category, heuristic search methods, where the probably most famous one is genetic algorithms or other evolutionary processes. But also, I would say reinforcement learning goes a little bit in here. The idea here is that you have one or more, what you say, individuals, instantiations, and then you randomly perturb them and see if it gets better or worse, and pick the ones that performs better and continue to perturb them. What can I say? These have different characteristics. So let's see. So they might be slightly suitable for different tasks, and some things you should consider when selecting which model should you use is, of course, one thing, the amount of training data. So I can go back to the previous slide here and say that neural networks, they are famous for being very data hungry, especially the deep ones, of course. So where you might need millions or more training samples for a good result, whereas sometimes in real world you don't have so many. In most cases, you don't have very many training samples. So then, for example, the case-based methods or the statistical methods are good. There might be good alternatives there that are not as data hungry, for example. Other things to consider, the ability to handle missing data. In the real world, you might have some unknown values in your data, and some of the methods are not as good at handling that, others are. Again, I would point at the statistical methods. They are usually good at handling unknown attributes. Invariances like time series, sound, images, and so on. And this is where they must be handled. And then there are specifically, I go back again, specifically, this is where the neural networks, there are specific the convolutional neural networks for images or transformer networks for sequences and so on, that are very performs well. There are other methods as well, of course. Again, statistical methods for Markov chains and such for time series. What kind of task do you have? Is a supervised or unsupervised task? With supervised tasks is typically classification when you want a class label as output, or regression when you maybe have a continuous value output. Whereas on the unsupervised side, there is usually anomaly detection is one of those when you don't have any class label, but more want to know if a new sample is different from the samples in the training set or unusual. And clustering, where you, again, may not have any class labels yet, but you want to categorize the training data into different groups that are different in some way. Yeah, and then of course the computational complexity versus speed, because some of these are, if I go back again, the case-based methods, they are very easy to train because essentially you just stack the training data up in a big table, but they are more intensive when you get a new sample and you got to compare it to all those saved training data to find the closest one. Whereas, of course, artificial neural networks takes a long time to train, but if it's not very deep, and if it's doesn't have billions of parameters, it's pretty fast to use them. You just have a lot of matrix multiplications. And then there are intermediates. You have statistical methods that are one pass, so they are quick to train and quick to use, for example. So there's a lot of considerations, and there are more than I have put here. But maybe the important point is the last point here. Just don't blindly select the best one. Don't try try several ones and pick the best one. You need to understand why it works or why it doesn't work, because typically it might be some small detail in the implementation. You may have missed some assumptions or some property of the data, so you should maybe recode your data. Maybe you can tweak it to actually make it work better if it didn't work. And did it rely on some assumption that you weren't aware of or you didn't think of? Or does the data need you to make some assumptions? So it's very easy. There are examples. Shall I tell an example? Yeah, there are many examples, of course, of people just testing 2 or 3 methods and saying, the other week actually, someone noted, what was it? Yeah, a Gaussian process model does not work as good as a linear regression model. And I was just, come on, this problem is not linear. No way a linear regression model can work better than a Gaussian process. And well, the performance shows it better. And then when looking close at the methods in scikit-learn, it was actually not just a statistical linear regression. It used what was it called? Damn, I don't remember what it was called now. I should have prepared this example better. I just took it on the fly. It was kernel based. They made the method had built in that instead of just using a linear regression on the input features, they first expanded the space by representing all the samples as kernels, and then they get a highly non-linear method that could handle this complex space, quite similar to the Gaussian process, which also kind of make kernels around each training pattern. So suddenly it was not a simple method that they claimed, linear regression works better than Gaussian processes. No, that was a misunderstanding, because they did not even care to figure out why did it seem that one method works better than the other. Okay, back to the to my script then. So uh, uh, this is about think what method to select and understand why it works. Any questions on that, by the way?
There's one question here in the HackMD. It's being written now. So what method works best for synthetic data, particularly for genetic sequence data sets?
And that's a difficult question. So I will refrain from asking it because there are there might be some. It's very difficult to generally say for this method you should use this. Synthetic data is a whole chapter on itself. I can talk a long time. It's about how to possible problems with synthetic data and how to handle it. But I can't answer really. I need to one needs to understand the data and the generating process. If it's maybe, yeah, right now transformers are very popular. I would try a transformer architecture if it's generative, if it's a sequence data. It might work, but I have no. It's impossible to say from that. It always requires. There are no different rules of thumb, actually. There are a few ones I mentioned with the number of data, but in general, it's very difficult to say exactly which works. So maybe I will continue, and maybe the following will cast some light of how to think when to selecting the method. But I'm sorry that I can't give a straight answer immediately. So instead, I will now start to go back into the data pipeline, the data cleaning, fusion, and pre-processing things, because it all comes down to understanding, also for answering which method should I use? It comes down to understanding what data do you actually have. So most machine learning models, of course, they assume that you have some kind of standard format. You have a number of features, and maybe if it's a supervised problem, then you have a class label or an output value. And so you have one sample per row, and everything is filled in and so on. So it should look neatly like this. However, real data never looks like this. So you have to produce this kind of format for the machine learning to work. So the data must be, you must select which data should I have. You must clean out noise from it. You may have to fuse together different sources with data, and you need to carefully think about the representation to use of the data when you feed it into your machine learning method. And this is a step that typically takes a large part of a machine learning study. Not necessarily of MLOps, because I would argue that the last step, the deployment, takes the longest time in MLOps. But the second most time is in this data processing thing. And let's see what I should say. So if we are lucky, the data is, if we are very lucky, that's not always the case. The data is well structured in a normalized database. So then you have typically a lot of different tables, and they have relations to each other, and some are one-to-many relations and so on. And each of these tables might look neat, like the table we want to have, but most of the tables are not related to the thing we are interested in, the output value, so to say. So these must be flattened into the format we need. And this might be quite tedious, because if it is well structured like this, typically you have indices that connect the different tables to each other. So it should be possible to unnormalize it, if you like. If one of the tables actually contain the thing, the entity you are interested in and want to make the conclusions about, then you can usually flatten out and insert all the other rows related to this key index on the same row, kind of. But in other cases, you actually have to process the things in more advanced ways to find the relevant, to be able to flatten it. I don't have any example right now, but this is a tedious process to go through and try to find the correct data. And now there's typically a lot of irrelevant stuff in these structures. You need to pick the ones that really are relevant for your question and flatten them out. But sometimes it doesn't look like this. It's much more fragmented. You may have several different tables from different sources, and then it's not even certain that you have the same index, that you have the same. How do you know the individuals you're talking about, the ones you want to have one per row in your flattened data? Maybe they have different indices, and you may have to, that needed some work to connect them together. And even worse, the different sources, if you have time series or so, they might be sampled at different rates. So you may have to maybe extrapolate or calculate averages or something to be able to make them talk about the same thing, the same time period, the same entities and so on. And this is, of course, the problem of sensor fusion, when you need to connect these different sources. And that requires quite a lot of handcraft. So what should I say? So typically you might, this is a step that is not easy to automate. Also, this is about the understanding of the different data. But once you have understood what to do, you want, of course, to automate the translation from this data structure or the several fragmented data structures into this flattened format. That you need to do. Also, to cleaning. Real data is never clean. So let's look at some things that may happen. Missing data, I already mentioned. Fields that are out of sync. They might be this is kind of artifact. It can mean several things, like they have. It may mean that in a time series you have. It takes time. So the measurements are kind of offset a little bit in time, and then you have to maybe recover what. If you have a process, something that flows from one end to another, you may have to recover the timestamps of when were they actually the same mass piece of mass that flows through the process. What did this experience and so on? But also but maybe more errors, noise, and so on. Misspellings. Someone may have the brilliant idea of storing special meanings as special values, like temperatures of -9999. That's surely everyone will understand this is not a temperature. So we can use it to say that the sensor is offline, or something else, like an error message or so. And that will hit you if you try to analyze your data in the preliminary phase and try to calculate an average temperature, for example. So you just take the mean value of that column in your pandas data frame, and then these special values, if you're not careful, will be weighted into the average and shift it significantly. The same with spikes. If there are really absurd values in the data, any average will be clearly ruined by that. Then we have drifting sensors. I have seen this kind of something that should be the percentage of a content, and it was the sensor always produced numbers between 0.3 and 100.3. So clearly a small drift there. This is also a nice example that someone has, we have data 10 years from 10 years, but 2 years ago we changed the format slightly so this column doesn't mean this anymore. It means something slightly different. So then you suddenly sit there with a data set that has changed meaning in the middle, even if it's a slight change, even if the conceptually is the same, it might be need you to actually do something smart with those columns and process them differently before this date from after the date to make them exactly the same, the interpretation the same in the machine learning. Inconsistent data, irrelevant data, of course. So actually I put together, this is a table of different things, different artifacts in data. So this is I have put together, this is a potpourri of several artifacts put on one slide, but it looks like it's one data set, but they were not encountered in the same data set. But it's just as to illustrate what can go wrong. So the first attribute here, of course, that's a date format. You can see it's a date, and then suddenly there are some really ancient times, data from 1858. Yeah, that's great. They have really been collecting data for 150 years here, until you notice that, of course, this date, that is represented as 0 on Microsoft systems. If it had been a date that is 1970, 1st of January 1970 instead, then you would know that's a 0 date on a Unix machine or Linux. So it actually means there is no date. The date is unknown when this occurs. And of course, it's easy to handle, but you must be aware of it. The second column is a neat example also. What happened here? Yeah, you have values that are quite stable around 12.28 somewhere with some noise. So they are quite stable values. And then suddenly there pops up a value that is 10 times less, and later there is a huge value popping up here. And yeah, that may happen, of course. You have the data changes widely in magnitude. Nothing very strange about that. until you look at the decimals and notice that, come on, this 1.22823, it's kind of too similar to this 12.2824, and also this one, 12.2821. Is it just the decimal point that is the problem here? And probably it is. So I think these data, they have either been input manually. These are the real data we got. Either someone had manually written them in, or possibly they had used some OCR that occasionally from some paper with some speckles on it or something. So the OCR got the decimal point wrong here. So that is something surprising things that might happen. And then attribute number 3, it was, as I said, the use of special values to mean something else when they actually want to say something else. Yeah, that should also be caught and handled appropriately. What it says, here is a numerical attribute, but suddenly there is a string in it. So is it numerical or is it not? Is it symbolic or numerical? And in this case, I would say it's numerical, and the strings here should be just considered as, in this case, error messages, obviously, but it could as well be replaced by a missing value or something. Or the error messages should have had their own column with just the error messages next to attribute 4. And then final attribute 5, it's an example of a free text value. These are abundant in industry still. Maybe they are less abundant, becoming less and less, but there are still a lot of free text values, and then suddenly there might be different spellings. Sometimes there are abbreviation dots, sometimes not. Sometimes it's capital letters, sometimes not, hyphens or spaces. Yeah, they might abbreviations. So and that's of course tricky to handle, to figure out when it's just like this. It's not really a sentence. If it even were, it would be easier if you have, say, long free text messages. Then you can nowadays use a language model to create an embedding and then feed the embedding into the next layer, kind of. But with this kind of short notes, even that is very difficult to figure out what are the same here. Okay, just some examples of why this is difficult to fully automate in a sense. But nevertheless, yeah, okay. First, next chapter, missing data. I mentioned it now, and it's obvious that from this data table, some of these values you would like to input as missing data, like these error messages in column 4 and the strange special meaning data in column 3 here. What should you do with missing data then? And there are different methods. So maybe one should start with the last question here, the important question. What actually does it mean when there is a missing value in your data? Because it doesn't mean there is not one interpretation of it. It can mean one of several things. For example, it can mean that it can mean that it's unknown because we didn't try to measure it. So for some reason, but that is actually different from it's unknown because the sensor failed. Because if we let's say, if the sensor failed, then the being unknown is then, it's not informative in itself. It's just that, okay, we are lacking this because the sensor was offline accidentally here, but supposedly the data is distributed as it would normally have been. So the actual value is independent of the fact that it is missing. But if we didn't measure it, maybe we didn't measure it because we didn't think it was important. And then it might be that it isn't important because we don't think the value is noteworthy in this case. And then actually the value might depend on the fact that it's not measured. It might, or it might be, specifically, it might be irrelevant value. It is not given that because it is not relevant for this case. Then you should not try to replace it with something else. Or it might actually mean the value, yeah, okay, the value is normal. So we don't fill in any value unless it is special in some sense. So which is it in these cases? And it's important to know if the unknowns is it informative to know that we have an unknown value here? Does that it itself bring information about the class or not? So then I can go back up to different ways of handling these missing values. So one way is, of course, okay, we require that samples have all their values filled in. So if one slot is empty, one feature is missing, then ignore the whole sample. We can't process it. That's okay to do if you have so huge amounts of data that you don't, during training, for example, that you don't have to consider the ones with a few missing values. They are noise, just ignore them. Then that's a good strategy. There is a whole school otherwise of how to impute missing values in your data, how to fill it in with something. So, and there you can say, either we fill it in with a default value or the average of this column, or you can have more advanced imputation techniques to try to predict what the value would have been given the other features in the data. Or if it's a time series with nearby measurements in time. But this is a lot of activities going on. What is the best way of imputing it? And then we have the opposite school that actually I am subscribing to. It's a typical, because I use a lot of Bayesian statistics and statistical machine learning models and then the typical Bayesian saying or principle here is that do not invent data that you don't have. Use the data you do have. So that says if you have a missing value, you should not try to guess because it can only get wrong. So try to use a method that does not assume any specific value on the missing value slots. You typically integrate overall possible values or something. So, and that's a statistical methods are good on doing that, for example. If this missingness is informative, that actually means something for the class, that the value is missing. Like it might tell you something that in some classes, in some output classes, some values might be more difficult to measure. Then it means that just that a value is missing might actually indicate that it might be this class, because this value is typically very difficult to measure if you have this class. And then you could actually add an extra column. Maybe don't fill in the missing values, but add an extra column with a 0 when it's not missing and a 1 when it is missing. And this column, you can then see if you have a correlation from this column to the class to see if it is informative. And this column will go into the machine learning and can help with bringing this information into the classification. But this is anyway something you need to think about because missing values are common. I have an anecdote to tell here. I didn't write it in writing, but just as a fun example of what might happen. So there was this, I was involved in this study in a medical setting, studying patients coming into an intensive care unit with different what's called traumatic brain injuries. They got a hard blow to their head somehow, maybe in an accident or so, and then they get into the intensive care. And the idea was, can we categorize these patients in severity, degree of severity, from those that are just mildly bruised, so there is no problem, they will survive, to those that are very, very severe cases that are with a high probability of dying from this accident, and something in between, depending on how severe are they. And we wanted to make a cluster model with that. And the first attempt was actually to use a built-in clustering method, I think a k-means clustering, I think it was, and it required all the features to be given. However, there were massive amounts of missing data in this clinical case. There were 90% of the data were actually missing, because the data was measurements made on the patient on admission to the intensive care unit. So the blood pressure is a simple thing that probably not was missing very much, but then a lot of other things, measurements on the patients, and 90% were missing. So the first attempt is actually to do this. Let's ignore the samples that have unknown values, so we can feed it into this clustering algorithm and see if we can divide it in patients, find clusters for patients that are less or more severely injured. And then it turns out it was fairly lot of patients. I think it was almost 2,000 patients. So around 2,000 patients in total. And when throwing away every patient with some missing data, there remained 6 patients out of those 2,000. And unfortunately, all those 6 patients, they were so severely injured that they all died. So this was not what this would not have been a good clustering model. It would just have been one cluster. Yeah, everyone dies, kind of. So, and here I can just stop to. We did solve it. We did. That was the first attempt. So we did something else, and finally we got a very good clustering, finding 6 clusters of patients and so on, and it's published and everything. But I can, if I may ask you, just reflect a little bit and raise your hand if you have something. What should you have done? What ideas? How do you think you should have done with these missing values in this case with massive amounts of missing data? I'll give you a few seconds to think of it. Anyone wants to? We can, as I promised, we can cut it out in editing if you want to say something.
I'm also writing the question in the HackMD document.
Yeah. Has anyone come with a proposal how to handle this massive missing value case? Or do you want me to spoil it?
It's coming now.
It's coming.
Yeah.
Wait a bit more. David, you have to point. You have to read
Yeah, I
them
will,
or tell the people to talk out loud.
So maybe I can also do that. Someone is asking, are we saying that everyone is missing the same data?
Everyone is no, if everyone was missing, if there was a column missing for all, we could just ignore that column, the whole column. Yeah, that would have been easy. But that was unfortunately not the case. They missed different values.
Someone is saying try to put default values for the missing values.
Yeah, actually, that's quite good. That is what worked for half of the missing values, approximately, were of that kind, because and you should not say insert the average value. That would be wrong. So I can explain what we did for say half of them. Some of the values I didn't reveal but some of them, if you get a blow to your head, really bad blow, then maybe there's a damage that makes that half of the brain, where you got the blow, may be swollen. And then there is something called the midline shift. So if you look at what is it called? This CT scan or something. You scan your brain and you will see that there is some millimeter shift between the brain halves, kind of. Then you insert that column that, there is a 8 millimeter shift between that one brain half is swollen, so it presses on the other one. So it reaches into 8 millimeters into that half. Then you fill it in. But if there is no shift at all, then if the shift is 0, then you don't fill it in. Then it's not relevant. Or maybe a patient comes in and immediately the problem is not that it's swollen in the brain, it's some other problem. Then you don't even check this. So then it's unknown. And there a good default value is that, okay, if nothing is given, the default value is 0. It is not the average of the shift. Maybe the average of the shift of those that has a shift might be the absolute, of that might be 4 millimeters or something. That would be wrong to insert on all these patients that actually, because now it wasn't given because it was not applicable. There were no shift in the brain. So that was half of them. Any other suggestions has come in or questions?
Someone is saying you can predict values using an assessment made from previous or similar cases.
Aha. Yeah, maybe. That is, however, not what we actually did. Any other suggestions? I will tell what we did, but anyone else first?
Someone says group the samples that have the same missing values, but this is missing on the second part. What do you do once you've grouped them?
Aha. That's clever. That's closely to what we maybe did something similar. I will say, why would I not do the prediction based on similar cases here? Because it is in this case inventing something that is not there, creating something. If each of the values are informative, and we are having patients and we want to actually be sure that we give them the best healthcare and so on, it's scary to try to invent values that are not there. Yes, similar people usually have this. So I would instead go for the second one, that is, if I understood it right, you can group the ones that have the same. Maybe the idea is, if you group the ones that have the same missing values, remove those columns from those patients and make a special machine learning model based on those. That is almost what we did. We used a Bayesian statistical machine learning method that could handle missing values, and that is essentially what it does. If it is missing, it will only use the other attributes and not weigh in the attributes that have missing values. But if the values are given, then it will weigh in those values in the conclusion. And this finally worked. So that is what we did. Half of the values could be filled in with default values, not averages. None of the values were actually predicted. And we used a method that could handle the remaining missing values as just don't, there are no information, so don't, just use the ones that values you have. Yeah, so that's what we did. And has there been any other comments before I go to the next section?
There is another one. Make an interpolation, extrapolation if data is missing in a column. If a
That is a
complete
filling
column
in.
is missing, then fill the column based on other column inferences, typically physics-based inferences.
Yeah, so you can have physics-based. If there is a clear relation between the columns, maybe a physics-based model that's one way of filling it in. Yeah, but it is difficult when you have these massive 90% missing actually, because most of them are missing. Because of course in healthcare it's expensive or painful to make a test, so you don't make all the unnecessary tests, and that is why it was so much missing, because different patients have different problems and different relevance tests to take on them. So only on these 6 patients that were really, really bad, they actually measured everything. And that's the reason for this this case that they all died. They were the really bad, hurt ones. So this is a kind of health data might be special. It might be easier to make use this prediction to fill in values in more industrial data, actually. But yeah, there are different ideas. Should we impute or should we use a method that can handle the unknowns? I will go on. Data representation. Why is it important to select a representation for the data? And you might think that now in the era of deep learning, you need not care about this. It's better to feed in, you have probably heard it, better to feed in the raw data and let it find the internal representations itself and to try to engineer some special representation that might not be the optimal one. However, I will dispute that a little bit, but let's see first. The claim is that actually the exact choice of method is less critical than the choice of representation. If you get the wrong representation, no method, not even the deep learning methods, will manage to do it. But if you find a really good representation, maybe even a simple model might work. So, so once it's better with a simple model, keep it as simple as possible is one rule of thumb here. Because if you have limited amount of data, you should hope to have a small number of parameters as well. So you want to keep it simple. And by selecting, if you know you have some structure, something that you can some pre-processing you can do to actually simplify for the model, you should do it. It could save you the need for massive amounts of training data otherwise. So while it's true that do I have a anecdote here as well, actually? Let's see if I have. Yeah, I have it on the same. I have it on the next. I will tell an example in the next. And this finding a good representation requires a lot of domain knowledge and problem understanding, of course, to figure out what is the best. So there are some examples here, and time series data is one example. And this is where I was gonna tell this anecdote again that maybe, yeah, here. everyone says that with in a neural network, if you just add one more layer, you could if you have a time series like a sound, if you have sound, it's natural to use a Fourier transform or wavelets or something to get over to the in the frequency domain. And there might be more interesting features there than if you feed in the actual waveform itself. And then someone says, but Fourier transform, it's linear in the sense that you just weigh together the coefficients. It's just you weigh together these. You convolve it with sinus and cosinus waves, and that is a linear operation in the data. So with just one extra layer of a neural network, you would get, it could learn the Fourier transform if it needs it. So you should theoretically not need to actually calculate the Fourier transform of your sound wave and then feed the power spectrum into your machine learning model. You could feed in directly the waveform itself. And however, everyone that tries, typically if you do in industry, if you try this, it would work if you had enormous amounts of sounds. Sure, you could do it. But if you don't have it, that extra layer of the neural network you would need to train, that would require a magnitude more training data to figure it out. So by actually doing the Fourier transform, if you have sound and know that the frequencies are important, if you do this for it, you save one layer and a factor 10 of data requirements to actually do it. So while everyone says, it can do it for you, the network can do it for you, you don't need to do it. So far, I've only seen that you get better performance if you do the Fourier transform instead in the beginning. So that's just one practice. Sorry. Also, you can, if you have time series, you can use averaging. If you think that the signal is not in the fast sampling rate, maybe the signal is over more larger time scales, maybe you can use some Gaussian filtering of the data to get different time scales out. Also, differentiation and integration, that's also very important. Some time series are accumulated values and some are not, kind of. So by taking differentiation or integration of attributes in your time series, you will bring out other information than is just visible from the value itself. And that's a good trick to think about. Is the real information you're after, is it in the actual signal or in the differential of a signal or in the integration of it? Like if you have a trip meter in a car, the trip meter value will not be correlated at all with the speed of the car, but the derivative of the trip meter will be correlated with the speed, right? So you might find relations in the differential of it, but not in the original value. But on the other hand, the wear of the car might be how when it needs service and so on might be more related to the integral of a value or to actually to the trip meter value. How far have you been traveling than to the actual speed? So this is something that to think about. Markov assumption you can use for time series, that if you say that the most relation is to the previous time point, so maybe you should feed in not just a snapshot what it looks now, but maybe the previous point as well, and maybe make some statistical processing. Another thing that I want to mention is event data. That is also kind of special. How do you feed in that immediately? Maybe it is not every single event that should be fed in as one row in your flattened data. Maybe you should count the number of events in a time window instead and feed that in. Maybe that will tell you more. like if you have insurance data, maybe every single accident there's a random effect in when accident happens. So maybe you cannot predict a single accident just from some properties, but maybe you can predict the frequency, the risk of accidents given some properties. So maybe you should go for that instead. And invariances in general, in images, translation invariance, size invariance, and so on. And then there are, of course, as I mentioned, network architectures that can handle that, like the convolutional neural network is good to handle image data, or vision transformers as well nowadays, of course. But these are the things that one has to consider. There is another anecdote. Yes, okay, I know I will break for pause here, but I need to tell another anecdote. When these CNNs, the convolutional neural networks, were popular in the beginning, people were trying to do time series analysis. If they had a time series, they say, we can just plot the time series as a graph and then feed it into this two-dimensional CNN, looking at it as an image, and then it will make a lot of conclusions from it. And yeah, you could, but if you consider the actual invariances you have, in a time series, you have a one-dimensional time invariance that you can shift the signal a little bit back and forth. Probably it shouldn't matter exactly where you start timing it, but the shape is the important thing, kind of. That is the assumption here, but not exactly when it starts in time. You want to catch whenever it starts, kind of. So if you just chop it up in windows, it will not be invariant. You need to have a sliding window if you want to catch this general thing. So then maybe a one-dimensional CNN is much better. Or if you have several features, we can plot the features on top of each other and look at it as an image with a grayscale for the intensity. No, code it as a one-dimensional CNN with several channels instead of a two-dimensional CNN, because you do not have invariance across the channels. Typically, you don't. In an image, you have translation invariance in the x direction and the y direction. But in a time series, you typically only have it in the time direction. So then you should not use a two-dimensional invariant method. Maybe, let's see, concluding remarks. Finally, soon we are at the, at the break. So, final remarks here. Again, just like also Lodovico pointed to in the introduction, it's very tempting to do this manually. Yeah, all these steps, data selection, cleaning, fusion, and finding the representation. You look at the data, you see that, here are some outlier data. There are 2 outliers out of 1,000 sample points. I just remove them. I go into my editor and remove them. And this value, it must have been wrong. It says there is a missing period here. I go into the editor and put the period back where it should be. No, you have to write a script to do it, because this is not the last time you do it. It's not that you do it once and for all and now you have a clean data set and everything, you can be happy. No, you should design a method that can handle new data, possibly streaming data that will come at it in the future when it is actually deployed. So you need to write a script that does this for you. And again, every decision you take in this cleaning and selection and how you will pre-process the data, document it, because this is not the last time you will need to revisit it. You will have every new data set that comes, you will have to do it again. And you need to remember what you did and what did we actually decide. You may need to tweak it because it turned out not to be a very good decision after all. Then you need to go back and tweak it. So write an automatic script to do the entire cleaning, fusion, and pre-processing step from the sources you have, from this. Maybe it's a nor a SQL database or the different sources or streaming sources or whatever, make sure you can figure out how to filter out bad values, how to to connect the different sources, and how to transform it into the representation you want to feed into your machine learning model, all automatically. Any quick questions before we take the break?
One from the chat, not from the chat, from the document. When we are working in a situation where we don't have much experience with the problem, we don't know the data, we don't have a preliminary idea of which variables are important, we don't know about their correlations, are there any best practices we should follow to begin understanding the data and the problem?
And that is what I will talk about after the pause. So now we come to this thing, understanding the data and understanding the task that is so important, and which also was the question before the pause touched upon. So it's right, it's very difficult. It's difficult to do something with just an anonymous data set. So that's why this is the very, very first step, of course, in all machine learning projects, and specifically if you have in the MLOps chain, understand what are you gonna do. So first, there is on one level, on a simple level, of course, it's these kind of questions that are having the first bullet there. What kind of task is it? Classification, regression, prediction, clustering, anonymization, hypothesis, in system identification, simulation, visualization, blah, blah, blah. It can be, there's a lot of tasks, that much more than I have written here, that can where you can use machine learning, of course. So first thing is what kind of task is this? And an important sub question is, of course, is it supposed to be supervised or unsupervised, or maybe something in between, or will it be incrementally learning as it goes? So and a related question that I think comes on the next slide is there any ground truth at all if it's a supervised problem? But that's has to do with the data also. So and of course, so these are questions you need to ask yourself. What exactly is supposed to go in and what is supposed to come out? And then there should hopefully be a connect between the two, that the thing you want to deduce from the data, that there should hopefully be hints enough in the input data about that, because these methods, despite what many people out there in the society appears to believe, there is no magic in these methods. If there are no hints in the input of the output class, then it won't work. So, but on another level also is this question: how is it supposed to be used when deployed? What will actually be available then? Will the ground truth be available then for new situations that happen? Or will it not? Will the system be the ground truth? I mean, if you make a machine learning that is for some classification, is it supposed to provide the labels that will in the future be used as ground truth? Or is there a way of actually checking this in the future? So it is very often that actually when we make in a research setting, when we do just the machine learning part, try to solve a machine learning task, the setup is so different from the actual thing you want to do when you want to use it in the end, that it's it's not the conclusions you make from the research part of it is not really applicable to the reality. Do I have an example? Yeah, the typically is most of it has to do with ground truth, that in the research setting, you assume that you have the ground truth available and you can train it and fine-tune it with it. But then actually in reality, you may not have it. And then the entire setting that you assumed cannot be used. Maybe you cannot, you need to maybe retrain the method regularly in reality. And if it's very expensive, if you have spent a lot of manual labor for once and for all label a small subset of the real data with ground truth labels, then you will not have that in the reality then after this first explorative phase. So maybe you will need another solution altogether that is not unsupervised maybe. So this thing, how it actually gonna be used, is very important part of understanding the task, because it's so easy that you do something extra for this, the first initial training set that will not hold in the end. And another thing, another question here is, I go to the last one first. What is a good result? How are we gonna evaluate it? Is that has also to do with this ground truth. Can we tell if it's good or not? What are the metrics to evaluate it? Because that may affect how you actually design your method and which method you choose. And also this question, in research, you might feel, we have a performance here of 82% correct. That's great. It's better than chance, 50% chance, say, if it's a binary classification. 80%, 82%, it's excellent. Well, for actual production, you might want 99.9% accuracy. Nothing less is profitable. It's just not acceptable that 18% of your customers will be dissatisfied because they got the wrong conclusion somewhere along the lane. So that's also something that may differ from research and when you actually want to deploy something for real in the real world. But now I want to come to this. What is really the task as opposed to what the task owner believes? So if we get someone asks us to solve some problem, we might take them literally, and then it might turn out that this was not really what they wanted. And that's kind of, this is a tricky thing. So now I have to tell one of those anecdotes again. It was in my early, when I was young and green in machine learning, we got this task. We had this project together with an industry producing steel or steel components, and they had a problem that sometimes the quality of the output steel was, they had measured the quality, and sometimes they had 1% or so of the produced things could have scratches in the surface that could start rusting and so on. And so they wanted to predict in the production, what is the risk of getting these kind of damages? So then we got a lot of process data, and then we started analyzing, can we predict the risk of getting these small scratches based on the features we got from them? And it worked fairly well. We found some things that were correlated with the risk, so we could at least instead of just having, it's 1% all over, we could say that, for some components, we could say that for these, the risk are at least less than 1 promille. And for some components, the risk, we could say, the risk is almost 20% for this component of getting this kind of small surface damage. So we were quite happy. That was a kind of, what is it? Yeah, it's a 200-fold increase in the information, rather than say, everything, it's just 1%. No, you could say that these are very low risk and these are very high risk. And the most important attribute actually was the requested quality of the component. How tough steel should it be? Should it be a weaker steel or a tougher steel? Like some more hardened or less hardened kind of. And of course, maybe the less hardened or more brittle, some steel types were then more prone to these damages than others, naturally, because if they are harder, it might be less scratches and so on. So we could pinpoint that fairly well. So we were quite happy with the project. But then it turned out, of course, and that's obvious when you think of it, that's not what they wanted at all. They didn't want to know that one of their steel qualities are less prone to problems than another steel quality. They could have found that out themselves. What they really wanted was to do something about it. They wanted to find some factor they could control to get less damages. And that's another problem. That's not the same thing as predicting when they will have a surface damage, to figure out how to steer the process to avoid it. That's actually quite a different problem. So, and of course, now when I'm more experienced, I always keep this in mind, that what the customer says they want might not be what they actually want. That is actually, I have another example actually, similar. In the beginning, there were many customers that were actually coming and say, we want to find how the data are find relations in data and visualize those relations in the data. And that is very interesting and nice thing to do. But again, it's not the final thing they want. They want it for understanding their own data, but they want it for some following step to control the process better, or to make it more efficient, or to save some money. So this is just the first step to find relations. So it's better than to understand what do they really want in the end. And actually, as a final side anecdote, when people come to us, industries come and say, it's not so common nowadays, but it was once a while. They were saying, we have a big, nice data set here that we have collected over several years, but we don't know how to use it. Can you look at the data for us to figure out if we can use it for something? And nowadays, I say no to such assignments. We don't do that. They must know what they want before we take on the assignment. You can watch at the data how long as you like and find a lot of interesting stuff in it, but it's kind of, if you don't have anything concrete to look for, it's not worth it, really. That's what I would say. End of anecdotes. Let's go
Anders,
to
there's
yes.
a good follow-up question to this.
Yes.
So you were saying, what's the change in approach when going from understand what's happening, why it is happening, to find a way to prevent it?
Yes. And that is one of my favorite questions. It would, now I have to be, I think I will spend some time on that tomorrow, actually. rather than today. In the afternoon tomorrow, I will have a slot, and then I can talk a little bit about it. It's difficult because it turns out that it's to predict how something will turn out and how to control it, to be able to actually steer the process to control it and to get rid of problems in this case. They are, as I said, the very different tasks. And I have some, at least what I will say tomorrow, I will point to some differences between those and a little bit what you can do about it. And to spoil it, should I spoil anything? No, wait till tomorrow. Come back, listen in tomorrow, and I will at least give some hints, although I might not give the full answer because it is a difficult task. But at least I can give you a hint where to start looking. And then I go on.
Yes, thank you.
I just duck the difficult questions. But yeah. Of course, understanding the data is part of it. And that was maybe the question just before the pause also. How should we do when we get this data set? And my first question in the previous slide is don't take on anonymous data. Make sure you understand where the data comes from. That is the best, the generative process of the data. But if we somehow, when we have the data in any way, we need to try to understand the data. And then what is not in this slide, but actually my answer would be that visualization is always that's always a step here to understanding the data. I should have added it in the slide, really. That's the first thing. Look at the data. First, you can look at the numbers, of course, but then try to plot it. Plot time series. Make scatter plots. Find relations between different attributes to understand if there are redundant data. Try to sieve out columns that you see are not changing anything. They are not. They are just constant, or they are all unknowns, or so on. And this is a tedious task to actually manually go through the data set and check out what the different columns look like. But otherwise, so that's and maybe that is the answer of how to go about when you get some, if you get some anonymous data that you don't know, you have to start looking at it, visualizing it to get some feeling for it. But here also, there are more to this, to understanding the data. Of course, there is something, you may have heard about it, something called data readiness that I can just mention. That someone, it was several years now, pointed out that this, you could, it's very too common in machine learning projects that someone says, "Oh, we have a lot of data," and when you look at it, they don't, or the data is not so good quality, and so on. So the idea was to try to rate data according to three different aspects of it, the data readiness levels. So where the first question is, of course, that okay, what data and how much data is really available? When say, "Oh, we have a lot of data," and then it turns out it's archived on paper, and it's maybe free text, and it's a lot of so, and maybe it's somewhere else that is difficult to get hold of. It's in some other system and so on. So actually, the available data, everyone thinks they have a lot of data, but it's not always that it's accessible and available after all. But that is the first question, to find out when you get this kind of project where you need data, how much is really available. And then is the second question, okay, once we know what is available, what is the quality of it? I mean, in terms of missing values or noisy values or strange artifacts that things have changed every second year, so the meaning of the columns are not the same anymore. Or is it is it just free text and with very difficult to interpret stuff in it? So that's the second question to ask. And the final is, okay, so we have this data. It seems there are some quality columns really in the data that should be able to do something from. But is it the information we need to solve the task? Is it really, does it contain the hints we need to solve the task? That's the third kind of question. So these are, we won't go in more to detail into these data readiness, but I just wanted you to know that this is a thing, and these kind of questions is good to ask and good to lean on when you are getting data from some company to ask this. But then, of course, data can have different modality. And of course, if it's nowadays, there is a lot of, when you want to use your chatbots for anything, or your LLMs, there is a lot of text data around. Previously, there was more, tabular data is still the most common one, I would say, in industrial processes. That's the thing of everything we focus on here now. Today is more actually, I think a lot about tabular things, but also images and sound are typically modalities, and they should be treated in different ways, of course. And one need to figure out what thing, if there are images, are there objects in the images we want to classify, or are there more like just some flowing chemicals, and we just want to look for bubbles or texture or something? Is it the texture we are looking for, or the actual objects? That's a huge difference depending on what affecting which model we should use, of course. And if it's sound, do we want to recognize someone saying something, or is it noise or background frequencies we are looking for? That's also a huge difference how to process it. So all of these things is what you need to make clear. Then most machine learning methods, of course, assume IID data, independent, identically distributed data. But in reality, is it? For example, time series. You may have time series that slightly drift over time. Then they are not identically distributed, right? Or time series, by the way. So each time point is not independent of the previous time point. There is a time relation between the time points also. And similar event data, it seems that might be the thing, that frequencies might change over time. There you might have drift over time. There might be clusters actually saying, okay, it's not a simple distribution. They might be identically distributed, but you may have different clusters of the data, and the cluster frequencies may change over time. So you may have a shift in which cluster is the most common one, for example. Or if there are a lot of patients, for example, in healthcare, they are not the same. They have different metabolism, different characteristics, different age, everything is different. So in what way can you say that they are identically distributed? So then you need to, if you get this, of course, you need to convert it into something that is as IID as possible. So with time series, you can make a Markov assumption and feed in pairs of time points instead. And as if you have a Markov relation then and no drift, you can pretend it's IID, or it will become essentially IID. Or if you make a cluster model instead of a simple single model, then it's easier to handle actually clustered data, even if the cluster proportions changes and so on. So you can typically, if you think about it, even though the real world is seldom completely IID, this is when you think about it, you can typically transform it into something that is with simple tricks. Another thing to understand at this stage is, okay, as I think I did say in the previous slides, is the training data you have really representative for what you expect in the future when you deploy it? Because, and there I could, I think we are, unless if we were not running out of time, I could tell you some anecdotes there as well, how easy it is to use the wrong training data, which is not representative. And as I mentioned also previously, do we really have access to ground truth? Will we have access to ground truth when we put it into production? And then this important question, if we don't have enough data, can we cover up for that with something else, like synthetic simulated data or some physical models or some domain knowledge? And sometimes we can. I will not go into this all details today, so this is all you will get on this, but these are at least a lot of questions to ask in the process of understanding the character of the data. And that then leads us to then I will jump to the other side. Now I have been talking about the data pipeline, starting with this, understanding the problem, understanding the data, and then wrangling the data into a nice format so we can feed it into the machine learning. So now I will jump back to the machine learning pipeline and instead talk about these hyperparameter selection and validation and stuff. Maybe I should ask, is there any question? I go back here on this data pipeline. Any additional question?
There is
There is a
one
really
thing
good question. Go ahead, Lodovico.
Yeah, there is one just finished typing now. Sometimes we see a strong correlation between some features, but no real causal relationship. How can we spot those cases, and what can we do to prevent the models from learning relationships that are not true in real life?
That is also a very good question. It's actually very. We use some causal methods to actually try to figure out the causal directions and sieve out relations that are spurious and not causal. And that is one way, but it is also related to this other question that I ducked, that I may come back to a little bit tomorrow. I don't have the ultimate solution, but you have what you have done by identifying that this may happen. That's the first important step, that the machine learning methods might get fooled by these kind of relations. There is a strong correlation, but it's not causal. And I would say that is part of the solution. You need to identify which relations are actually causal. And to do that is tricky. I will not give the full answer today, but I will come back to this complication in some of the anecdotes and examples I will take up tomorrow. Although I might again not solve it completely, but it's a very important thing. So I will have some examples tomorrow as examples to watch out for, things you should, so at least you can know when you have this. Yeah, I think I will. Again, I duck it, but I will come back to the issue tomorrow. It's a very important issue, indeed. So now I will just end with this hyperparameters training and validation. So, of course, after training your model, you want to estimate the performance and the generalizability performance. I mean, you want to know how will it actually perform when you deploy it. Not any happy numbers from the research phase of this, or from the first phase of this. So, and the risk is, of course, with all machine learning, that you have the risk of overtraining the models. And that actually, even though some of the methods I listed in the beginning, the case-based, the statistical, the neural networks, etc., they have different, they are differently prone to overtraining, but they all have it. Sometimes, yeah, there are these methods that are claimed to, that you get if you use a support vector machine, it has no overtraining. And then after a while, the same author came with now we have a relevance vector machine. For sure, this one has no overtraining. And the thing is that even that one does. They all do, even though they might be less prone to overtraining. Some of them are more prone to overtraining than others. So this is the kind of thing, how to avoid overtraining. And actually, whatever the results you will get in your validation, it will always be more optimistic than when you actually deploy it. Unfortunately, whatever you do, so be prepared that however hard you try to avoid it, you will always get too optimistic results. I will say, so what are we doing? So now I will go into the practices. How should you do with the hyperparameter tuning in relation to training and so? And you know this, of course, that you should partition your data in 3 sets, not 2. Typically, sometimes you can get away with 2, but typically you need 3 sets: a training set, a validation, and a test set. And here's a caveat, because in some sources, the validation and test sets are mixed up in the naming. People call the validation set test set, and they call the test set validation set. So, but I will use this definition of it now, and I think this is the one on Wikipedia, and the one that I think the most common convention. But just be aware that at some places these terms might be exchanged. So training is, of course, the one you actually use when you train your model. But then you have this validation set that is used during the training phase. You use your validation set, for example, as a stopping criterion. If you want to stop, if you have a method that can be easily overtrained, you might want to stop it when it when the generalization doesn't get better. So then you check with the validation set how performance increases on the validation set. And when it starts decreasing on the validation set, then you should stop training, because then you're into the overtraining phase of it. But this is also, the validation set is also the one you should use if you want to fine-tune your hyperparameters. So then you can adjust the hyperparameters, use the training set to train your method, and evaluate it on the validation set. And then you can pick the hyperparameters that gives the best performance on the validation set. So the validation set is kind of part of the training in the training phase, but it is not the training set, of course. Unless in cross-validation, then you split up your training part of the set into a training part and a validation part, and then you do that, change that division, and again, it's the training and the validation set that you will play with. The test set, that should be held out through the entire process all the way to the end. And that is then until the first time you rip the seal of it and test your final proposed method on it. Then when you get a real feeling, the best feeling so far about the generalization performance that you can attain. Not before that. And when you have done that, you have rip the seal off it, then you shouldn't really use that test set again to test another architecture. Then you should have used the validation set and the previous set, the previous step, fine-tuning the hyperparameters and selecting the things. But so as soon as you have used it, it's kind of, then you are leaking information into the selection of the method. So you will now, if you start using the same test set repeated times, then you are searching for an architecture or a method that has the best performance on this specific test set, not necessarily the best performance on a new set of data. Just so you remember that. But it's very easy to do, and it's very, that is, people do this. They use the same test set over and over again, but they will no doubt get more and more select methods that are fine-tuned for this test set. And that is one way of overtraining to seep in. And I need to tell this also. I know the time is running out. I need to speak faster, but it's not many slides left now. There is a huge... I will wait to the next slide. Sorry, I will take this example on the next slide, really. So the important thing here, another thing that is very important, if you... this is what I said. If you select the model architecture and the parameters, don't use the test set. It is a validation set. That is the one. You may use the validation set to pick parameters, but this is should be considered part of the training and not the testing. And then, so I now list these things, some ways to guarantee overtraining. Is, of course, some of it, too few data samples. That will kind of guarantee overtraining, overfitting your model to those samples. Or if you have a too complicated model, with too many parameters. Now there is actually a modification here, because some of you may have heard that this is not really true. You can have, once you start getting more and more parameters, you will tend to have more and more overtraining. But if you get sufficiently much parameters, if you continue to increase in the number of parameters, you might get the opposite effect, that the overtraining decreases again. And that is, I would say, it's a little bit like ensembles. If you have so many parameters, then you get an even out effect instead. That it's like you have 1,000 times more parameters than you need. Then it's almost like a huge ensemble, 1,000 times ensemble instead, and that is decreasing the overtraining. So it's not as simple as I may make it sound here. But anyway, as a rule of thumb, if you don't want to go to that huge amount of parameters, keep it simple. And but this is an important thing that two similar training, test, and validation samples. If you have a time series data, don't do this. The first sample go to the training set, the second to the validation, and the third to the test set. And then the fourth to the training, one to the test, one to validation, one to training, one. Don't do that. They will be too similar, because a time series might move very, very slowly through the state space. So essentially, you will just have copied the same set 3 times, and that is worthless. You should instead take 1 month of data to the training set, then you take the next month, or even a gap maybe, to some validation, and then even a new gap for the real held up test, that it should be maybe far away in time to make sure that you generalize well if you want to really assess the generalization to some other data, because even time series might move slowly. So this is important thing. Information leakage. If you are careless, you might actually. There are many examples of that. I won't take them now. When actually the class information leaks into the features. Okay, I have to say some example because it's fun. You may have heard it before. I think it was using image processing to computer vision to classify breast cancer, I think. And you train this machine learning model on real pictures of these images of these mammography images of breasts that were with no cancers and those with cancers. And it was very good. It managed to pick out the cancers with almost 100% accuracy. And then it turned out when they looked, what does the model look at? Actually, in all the images they had used for training, all the images that were breasts with cancer had a small note scratched in a corner by the doctor who had said, "Oh, this is some," and the machine learning model only looked for that scratching notes in the corner, not the actual breast cancer lump of cells. So one should be careful not to have leakage like that. Non-representative data in the training phase. Yeah, of course, if you know that you have big variation and you have your entire data set you will use for constructing your model is all selected from one specific circumstance, then it will not catch the real variation in the real world. And then fine-tuning, we already talked about it. And then I will say this one, the final one, evaluating several models with the same validation set, same test set, I would say. Don't I mean the same test set there? I should have said test set, sorry. That's the one I want to say. There is a huge overtraining going on with all these benchmarks in the machine learning community, with everyone using the same benchmarks, essentially then polishing their models and their architectures, and the ones that win and the ones that get published, they are the ones that are most fine-tuned to get good results on those benchmarks. Think about it. That's a massive overtraining in a sense. It's not at all certain they will perform as well on real images or real, when moved to the real world. So again, concluding remarks for this, again, don't try to do it manually. It's not the last time you will fine-tune your parameters and so on. The parameter tuning is part of the training. It should use the same training validation set thingy, but not the test set. That's sacred. So provide the code to do it automatically, because whenever the data gets updated, you need to do it again. Or if someone out there wants to benchmark your method against their own, they will fine-tune the parameters in their own method very, very nicely, but use the vanilla parameters of your method. And then, of course, their method will win, right? But if you provide with your training instructions, do it like this to tune the parameters of this method to your new data set, then there is a chance that your method will actually beat theirs. So, and with that, the conclusions now of what I was saying in these pipelines, data and model pipelines. The most important thing, understand the problem you're working on and even the process behind the data. Select a suitable representation. That even the deep learning models will not do that perfectly for you. You need to know what you are feeding in, otherwise you will trip on it. And be careful with the validation, because overtraining will seep in. And finally, keep it as simple as possible, but still powerful enough to solve the problem.